This was 1996 AP Physics B exam question. So what's given is the cylinder, and the top cover is free to move. They heat up the gas. They give you the area of it and the height of it. They heat up the gas to 363 Kelvin and make sure that it is in full equilibrium. That means inside pressure is equal to the outside pressure, 1 atmospheric pressure, which is 10 to the 5th Pascal. And then they tighten up the cup on the top and let the gas cool down to 298 Kelvin. What is the pressure of the cooled gas? So if I'm solving for A, I need to find the pressure of the cooled gas. To find the pressure of the cooled gas, I need to see which kind of process it is. And in this case, it is isovolumetric process. The volume stays the same because they fix the cap on the top and the volume doesn't change. So I can use the gas law, P sub 0 V sub 0 over T sub 0 is equal to P final V final over T final. But because my initial and the final volume is the same, I can cancel them. And I have this expression left. Then my initial pressure is 110 to the 5th. And initial temperature is 363. You have to remember that if there is no delta T, then you have to plug in temperature in Kelvin. If there's delta T, you can do subtraction in Celsius without converting to Kelvins. But if there is only T, you have to convert it into Kelvin. Then I'm looking for the new pressure, for the final pressure. And the new temperature is 298. And here, if I plug in my numbers, I will find that the final pressure is equal to 0.82 atmospheric. So here is the new pressure. For B part, they ask us to find or determine the upward force exerted on the cap by the cooled gas inside of the can. And the force is equal to pressure times the area. And the area is given. So the new pressure is 0.82 atmospheric times the area that is given. Cross-sectional area is 0.005 meter squared, and my answer is 410 newtons. For C, if the cap develops a leak, how many moles of air would enter the can as it reaches the final equilibrium at 298 Kelvin? The atmospheric pressure and the atmospheric pressure. Okay, so we know the temperature. And the temperature did not change since it reached that temperature. And atmospheric pressure. So the pressure will change because some of the molecules will enter the lower pressure, current lower pressure. So this was the pressure after the temperature cooled down, right? So since volume and temperature are constant, we can use PV equals to nRT. So I have P initial, we're at 298, and V initial is equal to N initial RT. So your T does not change, and the volume does not change. but this pressure will change because now you will be at atmospheric pressure, and N is going to change because it's going to be new moles because new gas is entering. And you have P final, which is atmospheric pressure. The volume is still the same, is equal to, let me do this initial. The final number of moles in R and T does not change. So I can use a little trick right here. I can say, if I subtract one from another and take out R and T from my parentheses, so I can take V out, and I have P final minus P initial. I'm going to subtract it upward. So I'm going to say P final V initial minus P initial V initial is equal to the same R and T I can take out, and I can say N final minus N initial. So the volume is so the volume right here, I do not know what the volume is, but I have my area and my height, so I can find the volume. So what I have is V sub 0 delta P is equal to R T and delta N. And they asked me to find how many moles of gas will enter. So by how many the change of the moles, right? So I have the change of the moles is equal to delta P. V is the area times the height, and divide by RT. Delta P is atmospheric minus 0.82. Yes, I have new pressure is atmospheric, and the old pressure inside before the gas leaks, or the air leaks, is 0.82. So that gives me 0.18 10 to the 5th. Then I have area times the height, and again here is area on the top given in the problem, and here is the height. I'm going to plug in the number. Gas constant is 8.31, and the temperature is 298. So if I plug in my numbers, delta N is equal to 545 10 to the negative 3 mole.